Are ice cream sellers evil? Probably not. Well, at least not all of them. But I can totally imagine a situation where the price of the ice cream goes up whenever the temperature outside goes up. And if it's indeed the case, we can see a plot like this. Here on the x-axis we have temperature, and on the y-axis we have the price of the ice cream. And each data point is, on some particular day, we measured the temperature, we asked some ice cream seller about his price, and we plotted this data point in the two-dimensional plane. So you can see that these two variables are strongly correlated here and related to each other. Can we exploit this closeness of this meaning of these two random variables to each other? Well, we may say that these two variables are so related that you can use one to measure the other. For example, if you want to know your temperature outside and you forgot your thermometer and also the smartphone, you can ask your closest ice cream dealer and for his price and compute the temperature from that. Which basically means that these two numbers are so related that you don't have to use two. You can as well use just one of them and compute the other from the first one. Or if you put it a little bit differently, you can draw a line which goes through your data and kind of aligned with your data. And then you can project each data point you have on this line. And this way, instead of two numbers to describe each data point, you kind of now can use one, the position on this line. And this way you will not lose much. So if you look at the lengths of the projections, so how much information do you lose when you project points, and each blue data point is projected on the corresponding orange one, you see that the lengths are not high. So you keep most of the information in your dataset by projecting on this line. And now instead of this two-dimensional data, you can use one-dimensional projection. So you can use just the position on this line as your description of the data point. And it's just another way to say that these two random variables are so connected that you don't have to use two. You as well may use just one to describe both of them. And this is exactly the idea of dimensionality reduction. So you have two-dimensional data, and you project it into one dimension, trying to keep as much information as possible. And one of the most popular way to do it is called principal component analysis, or PCA for short. And PCA tries to find the best possible linear transformation, which projects your two-dimensional data into 1D, or more generally, your multidimensional data into lower dimensions, while keeping as much information as possible. So PCA is cool. It gives you an optimal solution to this kind of problem. It has analytical solutions, so you can just write down the formula of the solution of the PCA problem. And this analytical formula is very fast to implement. So if you give me like 10,000 100-dimensional points, I can return you back the same points projected to 10 dimensions, for example, while keeping most of the information, and I can do it in milliseconds. So it's really fast. But sometimes people still are not happy enough with this PCA and try to formulate this PCA in probabilistic terms. Why? Well, as usually, formulating your usual problem in probabilistic terms may give you some benefits, like being able to handle missing data, for example. So in the original paper that proposed this probabilistic version of PCA, they tried to project some multidimensional data in 2 dimensions. So you can now plot this data on 2-dimensional plane. And they then tried to obscure some of the data. So we introduced missing values into the data. They thrown away some parts of the features. And then they projected this data set with missing values again. And you can see that these two projections doesn't differ that much. So, which means that we don't lose that much information by throwing away some parts of the data, which is really cool. Like, right? We were able to treat these missing values and the solution doesn't change when we introduce them. So we're really robust to missing values. By the way, the paper where they proposed this principal component analysis is really good. So check it out if you have time and if you want to know more details about this model. So let's try to derive the main ideas behind this probabilistic principal component analysis in the following few slides. So first of all, it's natural to call this low-dimensional representation of your data. So in this example, one-dimensional position of each data point, each orange data point, to call a latent variable. Because, you know, it's something you don't know, you don't observe directly, and it causes your data somehow. So the position of your orange data point on the line, this TI, it influences where the data point will end up on the two-dimensional plane. So if it influences the position of the observed point, right? So it's natural to introduce this latent variable model where you have Ti, which causes Xi. And you have to define some prior for Ti, and why not to set it just to, you know, standard normal. This will just mean that your projections, your low-dimensional projections will be somewhere around 0 and will have variance around 1. Which, like, why not? It's a nice property to have. Now you have to define the likelihood, so the probability of X given Ti. And how does X and Ti connected? So how does this one-dimensional data and two-dimensional data is connected? Well, if you look at the orange, kind of orange two-dimensional X on the projection of X, then it equals to some vector times the position on this one-dimensional line plus some shift vector. So we can linearly transform from this one-dimensional line to two-dimensional space and get these orange projected points. Or more generally, we can multiply Ti by some matrix W and then add some bias vector B, and we will get our orange projections Xi. And this W and B will be our parameters, which we aim to train to learn from data. Okay, but this is orange points, right? How can we recover the blue points, the original data? Well, it's kind of, I don't know how to do it. I mean, it's impossible to exactly say where the blue point will be if you know the orange point, because you don't know how much information you lost, right? But you don't have to say it exactly. You can just model it somehow probabilistically. So let's say that the blue point Xi, which we observe, is just orange point plus some random noise, which is centered around 0 and has some covariance matrix sigma, which we will also treat as parameter. This way we are kind of saying that our blue observed data points are the same as the projection of our one-dimensional data into 2D plus some Gaussian noise, which means that we don't actually know where the blue points occur, but we expect them to be somewhere around the orange points, around the projections. Okay, so we have a latent variable model like this. So Ti causes Xi, and we have defined the model fully. So we have prior, P of Ti is standard normal, and we have likelihood. So Xi given Ti is some normal distribution also. Now we want to train this kind of model. So we want to find the parameters which are, for example, maximum likelihood estimation. Well, first of all, as usually, we will assume that the likelihood is factorizes into a product of likelihoods of individual objects. So we have n data points, and the likelihood is equals to the product of these likelihoods of data points. And then we can rewrite this marginal likelihood of individual object by marginalizing out Ti. So it's the joint distribution, P of Xi and Ti, and then we have to sum out TI. But previously we had sums, now we have an integral, because this latent variable TI is continuous. And to sum it out, it means to integrate it out. Note that in general this integral is intractable. And it's really hard to optimize this function, because we can't even compute it at any given point. The integral is intractable. So it's really cool that EM algorithm allows you to optimize these kind of functions, although you sometimes can't even compute them at any given point. But in this particular situation, you don't need that. So everything is normal, everything is conjugate here, which means that you can analytically integrate this latent variable TI out. So you can compute this integral, and it will also be a normal distribution with some parameters which you can look up in Wikipedia. And then you have a product of Gaussians, and you can analytically compute the optimal parameters. So you can take the logarithm of this thing, you can compute the gradient, and then you can set this gradient to 0 and find the maximum likelihood parameters analytically. And somewhat expectedly, we will find out that the optimal parameters for this probabilistic model is exactly the same as the formulas for PCA. So look what happened. We started with PCA, we interpreted it probabilistically, we found the maximal likelihood parameters for this probabilistic model, and they turned out to be the same as the original formulas for PCA. It's kind of unsettling, because we spent this whole I don't know, 10 minutes, and we didn't get anything useful from that. We get the same formulas as PCA. But it turns out that this probabilistic interpretation is still useful. So here we don't need EM algorithm at all, because we have everything analytical and nice. But if we change the model a little bit, then we will not be able to compute anything analytically anymore. But with EM, we will still be able to train it. So let's say you introduce missing values. You do not observe some parts of your exercise. Then you have more latent variables than you used to have. And then you can use, then you can't find the latent, you can't find the maximum likelihood parameters analytically anymore. But you can still apply EM, and it will give you some valid solution. So in the next video, we will talk a little bit about how to apply EM algorithm in this case.